we will compare the oscillation in the LC circuit with the oscillation of the block which is tied at the end of the spring. This is just a comparison. Block, when it was tied with the spring at the free end of the spring, that we have discussed in our 11th standard. Now see, the first of all their equations you try to understand. These are the equations of their rather second order differential equation of the oscillation of the charge and oscillation of the block. Okay, now see, this we have derived d2q by dt2 is equal to minus q upon LC, or it is written as d2q by dt2 plus q upon LC is equal to 0, and 1 upon LC is nothing but omega 0 square. So instead of this 1 upon LC, it is written as omega 0 square, okay, which is same equation as we have derived it for the block of mass m, which is oscillating with the frequency omega 0, which is kept at the free end of the spring. Then it is giving equation this, okay, d2x by dt2 plus omega 0 square x is equal to 0, and omega 0 square, there we have written as k upon m, where k is a force constant and m is the mass of the block. Okay, rather it is not having the square root, it is omega 0 square is equal to k upon m, or we can say omega 0 is equal to under root k upon m. Okay, so these were the equations which we have already discussed, okay, in our 11th standard. Now here F is equal to, we have kx in mechanics, where k is F upon x, means the external force required to produce unit extension or compression is known as force constant, that is force per unit compression or extension is known as force constant. Force constant, which is having its unit Newton per meter. Now same, we have V is equal to Q upon C. Corresponding equation of this equation in LC circuit is V is equal to Q upon C. So 1 upon C can be V upon Q, means for established unit charge necessary electric difference is 1 upon C. Okay, so there are certain quantities which are similar to that of the mechanics and electric system. They are given here. Mass is equivalent to inductance, force constant is equivalent to 1 upon C, distance x, or rather displacement x, is similar to charge q. There is, or dv by, rather velocity is dx by dt, here dq by dt the current. Mechanical energy is 1 half kx square plus 1 half mb square, potential energy and kinetic energy. Here we have 1 by 2 q square upon c kx square plus 1 half mb square. So this is the comparison. Okay, now there are certain, we call it approximation, which we have done in LC oscillation circuit. So for which two reasons the discussion of LC oscillations is not realistic. Now every inductor has some resistance. The effect of this resistance is to introduce a damping effect on the charge and current in the circuit, and the oscillations finally stops or die out. So every inductor is having resistance. What is the cause of that resistance? What will the resistance do? That resistance will finally stop the oscillations of charge. Even if the resistance were 0, the total energy of the system would not remain constant. It is radiated away from the system in the form of electromagnetic wave. Okay, in fact radio, TV transmission, all this depend on this radiation only. Now there is a comparison of LC oscillator circuit with the force damped oscillator circuit in mechanics, which we have studied. This is the equation of the forced damped oscillation, and this is the LC oscillation, or rather this equation of LC oscillator circuit. Okay, now see here the quantities which are similar, they are shown. First of all, their equations are shown, then displacement, then here it is charge, see here it is x, then here it is q, that is charge. Okay, time t, then time t is there, that is same. Then mass is replaced by self inductance, then damping coefficient b is replaced by, we can say r, that is resistance. Spring constant k is replaced by 1 upon c. Driving frequency is omega d, here it is omega. Okay, natural frequency of oscillation in the forced oscillation is omega. Here in electric circuit we have omega 0. Amplitude of forced oscillation is a, here amplitude or maximum charge is qm, and amplitude of driving force is f0, here it is vm. So this table just we have to keep in mind for the MCQs. Okay, now the next topic of discussion is transformer principle. Okay, transformer is a device which can increase or decrease the AC voltage. This is the device which is increasing or decreasing the AC voltage. The transformer which increase the voltage, that is called step up transformer, and the transformer which is decreasing the voltage is known as step down transformer. Principle is electromagnetic induction. Now here a construction is shown, okay, or rather it is discussed. Okay, a transformer consists of two sets of coil insulated from each other, means they are not in contact, they are isolated. Okay, now here the figure is given as shown in figure A and B, both we can see. Okay, the coil are wound on a soft iron core, either one on top of the other or on separate limbs of the core. So one on the top of the other, or this way separate limbs, either it is connected or one on the top of the other. This anyway they are joined, either one on the top or they are on the separate limbs. Okay, the primary coil is the input coil and the secondary coil is the output coil. So the primary coil is used as input, secondary is the output coil. The coils are wounded by the two ways core type, first of all, on which it is wound. Coil are wound on a soft iron core on separate limbs of the core as shown in the figure B. Separate limbs. Shell type coil are wound on a soft iron core, either one on the top of the other. So either this way or this way it is wound. Okay. So these are the two methods of winding the coils, and this is all about the construction. Okay. Now we talk about the working procedure of the transformer. How does it work? When AC source, try to understand when the AC source, first of all, say for example here we have the coil, here there is another coil, this is your input source, that is primary coil, and this is your secondary coil. Okay, this is for input and this is for output. Now here in the input AC source is applied. Okay, AC signal is given here. So when an alternating voltage is applied to the primary, the resulting current produced an alternating magnetic flux which links the secondary and produces EMF. So what will happen? Whenever the AC current is applied here, current changes. So flux associated with secondary also changes, which produces the electromotive force in the secondary coil by the principle of mutual inductance. The value of EMF depends on the number of turns in the secondary. So how much EMF is produced, that depends on the number of turns, as E is equal to N d phi by dt. Let an ideal transformer in which the primary has negligible resistance and all the flux in the core links both primary and secondary winding. If no any load is joined to the secondary, and number of turns in primary and number of turns in secondary are Np and Ns respectively, then electromotive force which is produced here in the primary is nothing but Np d phi by dt, and in the secondary it is Ns d phi by dt. Now we have put Ep is equal to Vp and Es is equal to Vs, where we have Vp and Vs are the voltage across primary and secondary. Okay, so we have this voltages across primary and secondary which are denoted by Vp and Vs respectively. So instead of this Ep, we shall write Vp and here we shall write Vs. So Vp is equal to minus Np d phi by dt and Vs is equal to minus Ns d phi by dt. Now you take the ratio, because all the flux which was changing with the secondary is same as that of primary, because the ideally flux is totally linked with the secondary that we have taken into consideration. So this d phi by dt will be cancelled out. You have Vs upon Vp is equal to Ns upon Np. The relation which is given above has been obtained using three assumptions. Okay, the primary resistance and current are small. The same flux is linked with both the primary and secondary, as well as little flux escape from the core, and the secondary current is small. So these are the assumptions on the basis of which we have obtained this equation. The ratio of number of turns to secondary and number of turns to primary, it is denoted by lambda, which is called the transformer ratio. If the secondary coil has greater number of turns than the primary, try to understand, secondary is having more turns, then what will happen? Voltage in the secondary will be higher, or it will be more than the primary, so it is stepped up. We can say this type of transformer is step up transformer, and the secondary coil which is having less number of turns, so number of turns in secondary is less than number of turns in primary, then the voltage in secondary will be less than voltage in primary, so the voltage will be less in the output, so it is step down transformer, or arrangement is called the step down transformer. The voltage is step down, or we can say reduced. Okay, now we move further using this equation of power for an ideal transformer. We have to prove that Ip upon Is is Vs upon Vp is equal to Ns upon Np. Very easy. Power is given by V into I. Input power is Ip Vp, where Ip is the current in input, that is current in primary, Vp is the voltage in primary. Then Is is the voltage in secondary, Vs is the voltage in the secondary. Now see, some energy is always lost, okay, but what will happen, the total amount of energy as such, whatever energy is supplied is say linked with the secondary, or we can say primary, whatever energy is supplied is linking to the secondary. So we can say that for ideal transformer, Vs upon Vp is equal to Ns upon Np, okay, where Vs and Vp are the voltage across primary and secondary. Ns and Np, as you know, it is the number of turns in secondary and number of turns in primary. Now these are the two equations, just we have to take the ratio. It can be done easily. Okay, Ip, okay, this is very easy. Ip Vp is equal to Is Vs, and Vs upon Vp is equal to Ns upon Np, and here from this equation we can write Vs upon Vp is equal to, Vs upon Vp will give you Ip upon Is. So we can write this equal to Ip upon Is. So we were this equation number 3, easily it is obtained. Hence I and V both oscillate with the same frequency as the AC source, and equation 3 also gives the ratio of the amplitudes of RMS value of corresponding quantities, that is voltage and current. Now these are the reasons the energy loses, because in our actual transformer, in ideal transformer, whatever input energy is seen in the output energy, or whatever is the energy in the primary or power in primary, is same as that of power in secondary. But in actual transformer, in our day to day life, it is not same, because there is flux leakage. Not all the flux due to primary passes through the secondary. Okay, resistance of the winding has some resistance, so I square r amount of energy is lost in the form of heat, so some energy is always wasted in the form of heat, so it will not totally obtained in the secondary. Eddy currents are there. The alternating magnetic flux produces eddy current in the iron core and causes the heating, and because of this some energy is lost. Hysteresis is also seen. Okay, the magnetization of the core is reversed by alternating current. When there is one cycle, it is magnetized, then again it magnetized, then demagnetized, again in the opposite direction of the current will again magnetize in opposite direction, then again demagnetize. So there is a hysteresis curve, or because of hysteresis we can say some energy is lost. Okay, transformer works on AC voltage, hence in each cycle the length of the core increases and decreases. As a result, transformer produces buzz noise. Okay, so some electrical energy is distributed in the buzz noise also. Okay, so these are the reasons in which the energy is lost in the our regular use of in the transformer which we are using in our day to day life. Okay. Now this is the use of transformer for distribution of power over long distance. Transformer can be used for a large scale transmission and distribution of electrical power over long distance. Okay, transformer is used in this power transmission. The voltage output of the generator is stepped up so that current is reduced and I square R loss is cut down. Wherever there is a power generation, say for example you have 240 volt and 5 ampere current, then the power is equal to this will be the power in our day to day home appliance, or we can say in our day to day home circuit. Okay, now see, if 5 ampere current is passing on a length of say 200 kilometer long transmission wire, wherever it is produced, and our home is 200 kilometer and 1 kilometer long wire is having say only 1 ohm resistance, then how much current? 5 ampere current and 200 ohm resistance, because 200 kilometer will have 200 ohm resistance. 1 kilometer long wire we are having say 1 ohm resistance only we have taken. So how much power will be dissipated? Power dissipated as I square R. So I is 5 square, and R is 200. So 25 into 200. So the power will not reach to our home. It will be, rather we can say, it will be vanished, or it will disappear within the wire itself, and it will never reach to our home. So what is done? I is made very small, say 0.05 ampere, and the voltage is made, say, what is our voltage? 2400. Instead of our voltage is how much? 240. Instead of 240 volt, we have say increased it to 100 times, because it 5 ampere current is made 0.05, means 100th part. Then our 240 volt must be increased 100 times to 240000. So power will be V into I, and power will be 24000 into 0.05, and that will be 1100 watt only. But now power dissipated in the form of heat when the current is passing through the long say 200 ohm resistance. Okay, then this power lost in the form of heat is I square R. So it is I square R. So R is 200, I square is 0.05 square. So this power lost in the form of heat will be very less, because 0.05 and square of it will be very small value, and multiplied by 200 will be very small. So power lost in the form of heat while transmitting will be very less. And when that power comes to our close by pole or somewhere transformer which is kept to our near to our house, that transformer will now increase this current to 5 ampere and decrease the voltage to 240 volt from 2400, rather 000. We have somewhere we are watching in our this poles also that 24 kV line. 24 kV means 24,000 volt line, means the voltage is 24,000 volt. So that voltage is brought to 240 volt, and power and the current is increased to 5 ampere, and that is supplied in our day to day, or rather our in home, and the appliances can run. Okay, so this is the concept of this transformer, and it is used for the reducing the power loss. Okay. Now these are some of the important uses of transformers. Small transformers are used in the radio, receiver, telephone, loudspeaker, etc. Also it is used in TV, refrigerator, air conditioner, computer, etc. for voltage regulator. Okay, for stabilizing power supply it is used. Step up transformer is used for getting large electric current for electric welding. Okay, step down transformer is used for melting the metal in furnace. Step up transformer is used for producing X-rays. And electrical energy produced in power station reaches to consumers through the transformer. So here our lesson number 7 is over. Now we shall discuss the numericals and illustration next time.